He's a third-year PhD student there with under the supervision of Joris, and he will talk about Euler approximation schemes for PDMP. He's happy to take questions also during the presentation, so feel free to unmute yourself and talk, maybe, or raise your virtual hand if you want. But he will also take questions at the end. Also, the talk is being recorded, so if you don't want to be recorded, just switch off your video and possibly switch off your microphone as well. Thank you, Andrea.
Thank you a lot, Alice, and thanks a lot for the invitation. It's really nice to be able to give this talk. It would have been nicer maybe to be there, but okay, that's maybe for the future. So yes, I'm indeed a third-year PhD student with Joris Bierkens, and I will in this talk discuss about some recent work I've been doing with together with Paul Dobson and Joris. And as you can see from this picture, this is a project we enjoy a lot working on. So the outline will be as shown here. I will start with an introduction to PDMPs. So basically, maybe also people who are not familiar with them can start from zero. We will see the Zig Zag process as a running example throughout the talk. Then I will quickly maybe mention also other samplers, but let's see. Then we will go to Euler schemes for PMP, so approximation schemes, and then we will motivate why we need them, in which cases. We will then go through some theoretical results for such schemes, strong error kind of results, weak error kind of results. Then a very quick numerical experiment, and then some extensions to what I will talk about in this talk, some things I have no time to discuss, and some final remarks. Okay, let's start with the first section of the talk. So PDMPs are a very wide class of stochastic processes that were introduced first by Mark Davis in 1984. And yeah, these can really be used to model phenomena, for instance, in biology, and lately they have been studied quite a lot for MCMC purposes, so when we want to sample from some target distribution. So we will denote a PDMP by ZT in this slide, and this is a stochastic process on a state space E that we can describe by its generator. So this is the general form of a generator of a PDMP. And then the first thing we can observe is that we have two parts in the generator. We have a first part that we can see as a deterministic part, the deterministic dynamics of the process, because these are indeed piecewise deterministic. And then we have a second part which handles with the jumps, with the random jumps that make this a random process. So there are indeed three important quantities in the generator of a PDMP, and then we will see what they mean. First, the deterministic dynamics, and these are described by this vector field capital Phi. And indeed, basically, the meaning is that, we will move, let's say, with velocity phi of z locally, let's say, for a small time step. And then we have a second important ingredient is this lambda here. Lambda is we can call it jump rate or switching rate. I will call it in different ways maybe throughout the talk. And this is what really will characterize the probability of having a random event. And also then it will characterize the time of such event. And finally, the third ingredient will be Q, which in general we can think of as a Markov kernel that will govern what happens at event time. So we will have a deterministic part of the dynamics described by phi. Then at some random time that has a probability distribution described by lambda, we will have an event that is described by this Markov kernel Q. Okay, something more about this. Well, in general, we can solve the ODE we have seen earlier that describes the deterministic dynamics, and we can define a flow map, phi of t, that will then be very useful when we want to compute the next position, the next state of the process. So basically what this means is that, as I wrote here, okay, we're starting at state z at time 0. And if we want to follow the deterministic dynamics, well, we can simply apply the flow map. And t indicates just how much time, for how much time we move according to these dynamics. Then we will have indeed to draw, to sample, to simulate this random event that here I'm calling tau. And this has the probability distribution I wrote in the slide. Indeed, it involves lambda, our jump rate, and so it's the distribution is really determined by lambda. And interestingly, here we have the flow map. So basically, this would be ZS if we were moving according to the flow. The final thing is then what happens when we reach the random time. So at time tau, we will have a random jump. And indeed, as I said, this is governed by the Markov kernel Q. And as we see here, what we're doing is we're moving for time tau, starting at state Z. We move with the deterministic dynamics for this time tau, and once we are there, we will feed the Markov kernel with this input state, and then we will draw Z tau. So the state of the process at time tau just after the jump time. Okay, so this in general is how a PDMP would look like. Then let's see the Zig Zag process, which is I will use as a running example in a few cases. Zig Zag process is a particular PMP. As we see here, we have two parts of the process. This would be a ZT in our previous notation, and we have two parts, XT and VT. XT will be a position, will be the position of the process at time t, and VT will be the velocity of the process at time t. Okay, I'm sure many of us are familiar, but still, I would like to give a brief introduction to this process. We have that it lies in Rd times -1 + 1 to the d. So this is a d-dimensional zigzag process, and the velocity is a d-dimensional vector that takes values -1 or +1 in each component. And then in general, if we are thinking about Bayesian statistics, we would like to sample from a stationary distribution, so from a target, and therefore we would like this to be also our stationary distribution. And if we choose some objects properly, in particular it's the switching rates, we can then have a zigzag process that converges to this pi. Naturally, here I'm omitting that also the velocity part plays a role, but we care about really the invariant distribution of the position part. And psi here is our potential, and generally many properties are expressed in terms of it. So the generator of a zigzag process looks as follows. So we have again our two familiar parts. We will have our deterministic part here, and this just says, well, the position is moving with constant velocity v, the position part of the process. And here we have our jump part. In this case, we have actually d switching rates. Each one corresponds to applying this this operator to the velocity. Basically, fi acts as a flipping operator and flips the ith component of the velocity. And the key quantity, if we want to sample from pi, turns out to be this lambda. We need to choose it in this form if we want to converge to the correct stationary distribution. And in particular, this is the maximum between 0 and vi times the ith partial derivative of psi. Okay, so this would be is a zigzag process. Okay, then for me, the problem I would like to use as a motivation in this talk is the following. So we cannot, in many cases, or let's say it's not maybe correct to say we cannot, but it's very difficult in many cases, and in some we don't know how to do it, to compute these random times. So the next event time for a zigzag process would have this form. We would have to solve this infimum problem, and yeah, we have to find the smallest t such that this inequality holds. So the difficult bit in this expression is indeed at the exponent, and in particular, we will have to be able to compute this kind of integral. And in the previous notation, this is indeed this, so lambda along the flow. But in this case, we're moving only in the position parts. And okay, here also UIs are uniform random variables. And if we do that, the idea is that then we indeed have a tau I that has the correct distribution as we have indicated earlier. So this is a difficult thing to do. Okay, but let's see how it would work in 1D very quickly. So we would start from a position X. So here we have position on the Y-axis. And I think, yeah, here we start with negative velocity. Then the first thing we have to do will be to find the next switching time, right? Once we know the switching time, we can move deterministically, linearly in this case with negative velocity. Once we get here, we will flip the velocity and it will become equal to +1. At this point, we can sample the next event time, move deterministically again according to it, and so on. So this is the idea. And therefore, it shouldn't be surprising that we obtain this pseudocode for a PDMP. Let's say we want to stimulate this PMP up to this time horizon t, starting at z. Then let's initialize t to 0 and z0 to z. Then let's say here we're given zt, so the state of the process at time t. Then what we will have to do, as we have seen in the example for the zigzag process, will be computing the next event time, which means in the general case, indeed solving this infimum of, that includes the integral of lambda along the flow. And so interesting here, okay, we were starting at zt in this case. Once we have computed this tau, we can simply move deterministically for a time tau starting at position zt, and then we compute zt plus tau by drawing from the Markov kernel. Okay, then yes, let's update the time and go on to the next event time. All right, so I hope now we have at least a clear picture of what we would need to do. And importantly, there are at least 3 things we have to be able to do if we want to simulate a PDMP exactly. First of all, we have to compute the flow map. If we can't compute that, we don't know how to move deterministically. So this is the first thing. Then we also need to be able to draw, to simulate these taus, these event times. And the difficulty, again, just to stress it, is here in the exponent. We have this integral that it can be whatever. And third, we need to be able to compute the Markov kernel that we have to draw from at event time. And just to say about the flow map, of course, for zigzag, that was very easy because it's linear. The Markov kernel also was very easy because it's just a velocity flip. The difficult part was the simulation of the event times, but this does not need to be it's not the case in general. We can think of randomized HMC, for instance, in which computing the next event time is very easy because we have maybe a constant refreshment rate. The flow map is very difficult to simulate, and the Markov kernel is very easy. So there are different combinations, and it really depends on what we're considering. So the question I would like to try to give an answer to is, what if we cannot do one of the 3 above? What if we can't simulate any of these? What can we do? Okay, for the rest of the talk, until maybe the really last couple of slides, I will just consider the scenario of the zigzag process, let's say, but for a general PMP, but the problem is the same. So we cannot simulate exactly the switching times. Then in general, people have have been proposing to use a technique called Poisson thinning. And basically, it requires having some upper bounds of this form. We need to be able to upper bound the switching rates along the flow by some function ms. And once we have that, we can simulate a proposal for the next event time that we will denote by tilde by simply using rate ms instead of lambda along the flow. Okay, and then of course this will not be from the correct distribution unless we make an acceptance rejection step that in this case corresponds to acceptance with this probability, this ratio, and this would be how it works. Okay, but let's see. Let's comment a bit on this technique. So there are a few inconveniences. First of all, we need to be able to find this bound. And as we have seen for Zig Zag, lambda depends on the potential of the target. So it's if we change the target distribution, this will be different. We will need to find a new bound for every application we consider. Also here, you should assume that ms is easily integrable. But okay, maybe you can make a loose bound. You can find a loose bound that's easily integrable. Well, but that's again also a problem because then we have our acceptance probability that would be very small. And this is an issue because you would end up simulating many switching times, many event times that get rejected. And of course, computationally, this is very expensive. And so we don't want that. Okay, so let's then see what we can do maybe to solve this issue. So again, just to stress, in this case, I'm assuming we can simulate the flow map and the Markov kernels, but not the switching times. And so we can maybe take advantage of this simple idea. For a small s, we can maybe approximate lambda along the flow with the value of lambda at the initial state, right? And this seems reasonable to me, at least. And then once we do that, let's remember that the true probability of the next event time to be smaller than delta is given by this expression where delta appears here. Okay. Then we can approximate this probability by using a frozen switching rate, right? So by using this frozen switching rate. And therefore, we see here we would have the exponent is approximately equal to integral between 0 and delta of lambda z in ds. And therefore, we get our minus delta lambda of z. So this is the idea that we can maybe take advantage of, because of course, this is a very simple expression. And of course, this is valid as long as delta is reasonably small. But in general, I would also like to say that phi of s will be Lipschitz, or at least I think it's a very reasonable assumption. And therefore, for a small s, we're not moving that much. Okay, so once we have this idea in mind, what we can do is we can build a Markov chain z bar tn on a grid from for the time variable, and here I'm just assuming a constant step size. So we have step size delta. And we can build this Markov chain as follows. Let's say we're given the state of this Markov chain at time tn minus 1. Then what we can do is we can compute first an auxiliary variable, z tilde tn, which is obtained very simply by moving according to the flow, the deterministic flow for a time delta. Of course, starting at the position at the previous time step. Then two things happen, basically. Either a jump takes place in this time step, or it doesn't. Well, this will be random, of course, and the probability that a jump takes place is given by the approximation that we've seen earlier. So indeed here we're just freezing the switching rate, and then we have that probability of having a jump. If this happens, we can very simply use the auxiliary variable we have defined here. So this is equivalent to following the deterministic flow for a time delta, feeding it to the Markov kernel, and this will give us the new state of the process. Alternatively, with probability 1 minus the previous one, there will be no jump. And in that case, we will simply follow the deterministic flow and nothing else happens. We move on to the next step. So this is the simple idea. Let's see in particular for the Zig Zag sampler what this would mean. Let's say again we're given position and velocity at the previous time step. Then we can do the following. Immediately we can compute the position of the Markov chain at the next time step, because as we have seen, the Markov kernel for Zig Zag does not affect the position part. Therefore, this will not be affected by a random jump in any way, because we have seen we're just jumping at the, if we're jumping at the end of the time interval, of the time step. Therefore, this is already our definitive position. But then we will have to compute the event times. And in particular, okay, in this case, we have actually for I that goes from 1 to d, because we have d switching times per zigzag, we have to solve this infimum, where here again, this is indeed the integral between 0 and t of lambda at the previous time step, but simply lambda is frozen. So this is the only difference. Usually here we would have a plus s times v bar tn minus 1. But in this case, we're freezing the switching rate. And this turns out is very simple to compute, and this would be the value of the ith switching time, where ui are random variables between uniformly distributed between 0 and 1. And so we see then the switching rate appears at the denominator here. So it's the same idea, but we're approximating the lambda with a frozen version of it. All right, but then we have to establish which component of the velocity, if any, will flip. Okay, wrong one. And therefore we have to solve a minimum. We have to just select the minimum switching time, call the corresponding component I star, and then we will do the following. So we will just simply, if tau I star is smaller or equal than delta, then this means that a switching event has happened or is happening in the current time step. In this case, we will flip the component I star of the velocity vector, and this will give us our new velocity. But it can also happen that tau I star is larger than delta, so the largest switching time, the smallest switching time is larger than delta, in which case no event is happening in the current time step. We will just simply copy and paste the velocity vector from the previous step. Okay, so let's see it in a very simple illustration. And let's start again at x, but this time with positive velocity. Therefore, we know immediately what to do, at least for the position part, because indeed we know we will be here. Then we have to establish if a jump has happened for the velocity, and then we have two options. Either no jump has happened, in which case we will continue with positive velocity, or a jump happens, in which case we will flip the velocity. Let's say in this case we're, okay, and just to mention, no jump indeed has probability 1 minus exponential of minus delta times lambda xv. And this, the probability of jumping 1 minus that, so just exponential. Say in this case we don't flip, we will then continue with positive velocity. Again, we have the two choices, either we don't flip or we flip. In this case, we will update the velocity vector, and this would be trajectory, a possible trajectory in a 1D example. Okay, so we have seen the idea behind these Euler approximations of for PMPs. Seems reasonable, I think, but let's see if we can support it with some theory. And I will start with some strong error results.
Can I just ask a question before you go on?
Sure.
Why can you ignore two jumps between 0 and delta, let's say?
Let's say it's a choice. It's not, you can choose to do many things. And then I will refer to that later. Indeed, that would be reasonable also, I think.
Okay, thanks.
This is really like the simplest, this is the first idea we had, what we started from. And I think, yeah, to grab intuition, this is, yeah, easiest, but indeed you can have many combinations, and you can also let jump times be not just at the end of the time interval, but during. So many things are possible indeed. Okay, so okay, we will need a Lipschitz condition for the vector field, a Lipschitz condition for lambda, Lipschitz condition in expectation on the jump kernel. So a lot of Lipschitz conditions, which turn out to be very useful. The third one, yeah, it's pretty vague, but let's leave it there. And then, yeah, it's a bit more complicated than the others, at least to write down. And it also turns out to be difficult to satisfy in some cases. I'm referring to the bouncy particle sampler, but let's discuss about that later maybe. And then we also need that the process lives on a compact set for a finite time horizon. This, for instance, if you think of Zig Zag with velocities that are +1 or -1, this is true. And also we conjecture at least that this condition can be weakened, but at the moment we're not entirely sure, so let's trust this. Okay, then we can state the following theorem. We can denote by t the time at the end step, nth iteration of the process. So here we have indeed a constant step size delta. And then we have that there exist two constants, k1, k2, that only depend on the time horizon and not on delta. So here we're imagining a fixed time horizon, and then the number of iterations we need to get there is not important at the moment. Then we have this sort of bound. So let's see a bit what's inside of this equation. So by W1, what I mean is the Wasserstein distance order 1. So we have, very informally speaking, we have the infimum over couplings of this expectation. So we're comparing the two processes pathwise. And then here we're starting both processes at point Z. So we started them at the same state at time 0. This is a semi-group of the continuous time process, and these are the transition probabilities of the approximation. Okay, so I think a couple of comments on this result are in order. So we have the nice thing is this delta factor in front, and then we have that this part does not depend on delta. So the thing is that then when we let delta go to zero, we will obtain that the Wasserstein distance goes to 0 linearly in delta, or at least the bound goes to 0 linearly in delta. And then maybe not so nice thing is this the t dependence in this bound. So we have that here at the exponent, we indeed have a e to the t k1, which can be growing fast. K1 could be linear in reasonable scenarios, but I think this is more or less the same behavior you would expect, for instance, in some, if you consider the Hamiltonian Monte Carlo algorithm. It's common because this comes out of the proof, but probably it's a very pessimistic bound. And okay, and then the proof, of course, is by coupling here. and actually not a particularly insightful coupling in this case. So I will not go into much detail, but the idea is just we're coupling event times and also the jumps, the eventual jumps. Okay, then we can go into some weak error results. And let's start with some assumptions first. So the first one is that, yeah, this function, so lambda phi of s of z is Lipschitz in S. And if you think about it, this is quite simple for Zig Zag because we had psi here is a potential. And basically what we need is something of this form. Something like this. And for Zig Zag, it's not difficult to see that this is equivalent to the gradient of the potential being Lipschitz. Another thing we need is that the PMP in a way converges to the stationary measure with some, yeah, in this case we assume geometrically, but actually it's not a problem if it's polynomial. We can still have similar conclusions, of course, with some differences, but in any case for Zig Zag we know that it is geometrically ergodic under some conditions on the potential, and therefore it's not really a problem. A third assumption we need is that the effect of small perturbations in the initial condition of the process vanishes in time. And this for Zig Zag is equivalent to having derivative estimates for the semi-group, which is something that we can show. Yeah, but still a quite a technical condition. And also another technical condition, some moment bounds. But at least to draw intuition, this will be equivalent to asking that the expectation of, let's say G is the Lyapunov function for the Zig Zag sampler, for the Zig Zag process. Then we want a bound of this form, G evaluated in the approximation and not in the true PMP, in the true Zig Zag, is bounded. This would be more or less the idea. Okay, but let's see what we can show in this case. We call G1 a very wide class of functions, let's say, because it's bounded by the Lyapunov function, which grows very fast, so it's not too bad. It's exponential, so it's a pretty wide class of functions. And then let's see here what we have. So we have that's denoted by Tn, again time n delta. And then for all G's in this class of function, we have a uniform in time bound for the error, basically, we're committing. So indeed, here we have the expectation for the continuous PMP. Here we have it for the approximation. And we see there's no T dependence here. C can be, it basically has the Lyapunov function somehow. So it can be quite large, but still we have a nice delta factor. Also, some other things we can say are the following. So we can give a bound here of the expectation of G of Z bar at time Tn, the error we commit with that to the correct expectation of G, so with respect to pi. And the bound we have, again, we have a dependence on the initial condition here, and then we have a delta plus something that decays exponentially in T. And also, if we want to consider the expectation of a Monte Carlo estimate of the expectation of G, we have the third and final result of the slide. And yeah, we see we have a bound that's, we can bound this error by some constants, again, depending on the initial condition, times delta plus 1 over Tn, right? So it's going to 0 when delta goes to 0, and the time horizon goes to infinity. Okay, so these were some of the results we can obtain for this approximation we consider. Now let's quickly see a couple of plots just to draw some intuition, but it's a very simple Gaussian target, 50-dimensional Gaussian target. And here I'm comparing the continuous zigzag to some approximation for it, Euler approximations. And I'm showing on the y-axis the error in the first component of mu. So we're estimating the first component of the mean, and we want to see how the error that we commit decays in time compared to the continuous time process. In this case, yeah, it seems very nice, right? Because we have more or less the same behavior as zigzag. So everything is decaying. Of course, choosing delta that's 10 to the -1 still shows some maybe, yeah, but there's noise, so it's difficult to tell exactly. But a more clear behavior is observed if you consider the radius statistic. And in this case, it becomes clear that, yeah, you should take delta small. And if not, you can get, yeah, a bad error. But this is reasonable, right? So it's not that surprising, maybe. Similar behaviors can be observed also for the bouncy particle sampler. Okay, and then finally, I would like to discuss some extensions and remarks that either to this framework, or we will see, or maybe something slightly different. So for the purpose of this talk, we just made a choice. We chose to approximate the switching times by using a frozen switching time, right? So at each time step, we froze the switching time, and we did not consider what happened. So we're not letting the process move when computing the event time. But actually, there's no reason why we are bounded to that choice. But we can actually use any approximation lambda bar of the switching rate, as long as we have this kind of bound. So in a way, we need it to be order delta. This is more or less what's written here. So many choices could be made. For instance, for zigzag, and this, I think it's nice that we can do that. We could, okay, let's remember that the true switching rates along the flow would be given by this formula. So we have VI. Okay. What we can do is simply approximate the partial derivative of psi with a finite difference scheme. And then this would satisfy this kind of bound here. And yeah, still have to check how it performs in practice. But the interesting part is that then we wouldn't have to compute the gradient of the potential every time. And this would be, in a way, a gradient-free Euler zigzag algorithm. Then the strong and weak error results we've seen before hold also for non-constant step sizes. It's just for simplicity that I didn't consider that, but yeah, it remains valid. And then also, yeah, we can still prove the Wasserstein distance bound we have seen if we introduce order delta approximations of the flow map and of the jump kernels. And again, this is very interesting because we have just restricted, I think, we have just restricted to this scenario in which we have problems simulating the switching times. But we can also approximate every part of the process. If we have an order delta approximation, we can still have the same strong error result, really. Okay, then really a final thing I would like to say is indeed on the same line as allowing multiple switches per time interval. That's maybe even after this, but indeed, why not allowing for the switching events to happen instead of at the end of the time step, also at some midpoints, right? Because in principle, this is also a perfectly reasonable choice. And in this case, I've shown, let's say, a zigzag-like Euler approximation, and we see that here we have an event that's indeed in between this time interval, and here we have another one. So this would be sort of how it would look like. Okay, for this kind of scheme, and of course, let's say here I'm assuming that as we have seen earlier, we're simulating the event times, right? And then we have a value for it, and then we were checking if it was before or after the endpoint of the time interval. Well, then we can maybe let it happen at exactly the point we have simulated. So it's not a random point in between, but it's maybe a thought of, we thought of a rule like that one. That makes sense. Okay, in that case, if we assume that we can simulate the Markov kernels and the flow, we even obtain a bound for the total variation distance between the PDMP and the approximation. And this is because, again, we can use a coupling argument, but the nice thing in this case is that we can indeed couple the switching times such that with some probability, the two processes have a switching event at the same time. And so this is fine for Zig Zag and bouncy. So the conditions we would ask in that case would make it possible to approximate Zig Zag and bouncy. And the bouncy particle sampler, which I haven't really described, but okay. It's another PDMP. Then another interesting feature of this different scheme would be that we need weaker conditions to obtain the weak error result. And this, roughly speaking, would mean that, for instance, for Zig Zag, we don't need any derivative estimates anymore. I haven't written here, but we can also, of course, obtain the same Wasserstein distance bound in any case if we approximate everything, the flow, the kernel, and the event time. Still, we get the same bound. But the last thing I would like to say is that in this case, we can also obtain higher order schemes. And the key idea is indeed that if you want that, you need to allow for multiple jumps in the same time step. And the problem is that, I mean, the reason why we need that is that, yes, so having the process having two jumps is an order delta squared event. So if we want to somehow avoid having that error, we have to allow for this possibility. There are also some other technicalities there, but it's quite straightforward to show that you can obtain higher order schemes in this case. So, okay, yes, that's what I wanted to say today.